future reference. There's PowerPoints under that seat too. Not that matters, but there's a double PowerPoint. Okay. Just future. Alright, morning everyone. Okay, a few things at the intro today. Still the clinic slide. Yep, clinics happen daily. They're awesome. Redemptions, I admit we'll still allow a few days late, okay? But try and keep up with them, with the redemptions. Room changes. Hopefully you saw the announcement or the email. It only affects 2 tutes, and those 2 tutes are tomorrow's 10 to 11 and 11 to 12. So the 10 to 11 that's with me in LG59, they've pushed us upstairs to G28C. Your MyHub has changed. If you're in doubt, if you forget what room I wrote there, it's in MyHub anyway. Just your weekly schedule shows that moved. And Tuesdays 11 to 12, Ben and I have had to swap there. So I'm taking that one in W238 and Ben will take the 9 to 10. Okay, but anyway, the room changes are just Tuesday 10 and Tuesday 11. And another general thing there, we've got spots in, not all tutes, but a lot of tutes now. If anyone's in a tute time they don't like, just send us an email. If there's a tute you'd rather be in, it's pretty flexible. So just chuck us an email if you would like a tute swap. The other things, blank quizzes for redemption. I've stuck these up on Blackboard now. If you get a 0 in a quiz, or if you just miss a quiz, you can then pretend it was just a 0, okay? If you miss a quiz and you've got documentation or something, that's all in missed assessment tasks. You can still do it in week 13 if you've got a reason you missed it. If you just missed it and you'd rather not have a 0, you could still do a full redemption on that and get a 5, okay? 10 roll and get half a back. So if anyone wants to do a quiz mark redemption on a quiz they just didn't do, they're in Blackboard now, okay? So if you want to print any of them out, it's got the multiple choice answers already in there. You've just got to explain it. So redemption on a 0 if you want to do anything. Where are we at? This is just a check around the halfway mark. So week 6 is normal. Today's lecture is the last content of the mid-semester. Okay, so the mid-semester only contains A lectures, and today we do A6 logs. So next week will be normal. Just the content of next week. Lecture doesn't go into the mid-sem. Week 8 is our mid-sem. So in 2 weeks from today, we'll do the mid-sem here. It's 1.5 hours, so we'll just take up our 2-hour lecture slot with just the mid-sem, no content, just mid-sem. I'll get a revision paper up soon. Anyone that did this last semester, it's the same layout, 6 questions, 1 for each lecture. A1 through to 8, 72 marks in 90 minutes. So I'll get a revision paper out there which is going to be exactly like the layout of the final one, of the real one. It gets a bit more complicated after that, and again I'm just giving a heads up now. We've got a 2-week break after that, drop-ins every noon to 1. Week 9 sucks a bit, and of course I'll put out announcements and all that closer to it, but week 9 we won't have a Monday because there's a public holiday. We'll be off doing other stuff. So what I'll do is I'll post the lecture from last year, okay? So week 9 will be, they keep telling us to be, what's it called? Something about when you integrate online content. I forget the fancy word, but anyway, we're doing that. So it'll be an online lecture on that Monday, just last year's, okay? Because we're still having the standard tutes. Notice the tute that I've got Monday 4 to 5, I've moved that tutorial to Friday 11 to 12, and your MyHub will show that. If you can't make that, around the time I'll just say, let us know, and you can go in one of the other tutes. So if you're a Monday 4 to 5er, and that 11 o'clock time slot's not going to suit, I'll just get you to email me at the time, and we'll choose a different one for you. But anyway, closer to week 9, we'll talk about the changes. And I'm still going to put on a Friday lecture 9 to 11 in that week for anyone that didn't like the online approach or still wasn't getting it. I'll still do an in-person lecture that week. But it's after the tutes, but But so you've still got the option to go to one if you want to go to one. Apart from that, we've got some pretty normal weeks, and week 13 will be tutes only for us, no lecture. No new content in week 13, just tutes, revision tutes, a quiz and revision. So at the moment, what do we focus on? Yeah, we're heading towards a week 8 mid-semester exam worth 30%. So it's going to be well worth giving some effort into. Just quiz, lectures A1 to A6. Okay. Logs-wise. Logs could be totally new to you. And I think this is one of the, well, definitely the marks go up in this lecture. As in the quizzes on logs, it gets what we call bimodal. We'll talk about later. There's a hump here and a hump here. With logs, if you get it, it's really nice. If you don't get it or don't watch it, it's nearly impossible to guess. It's not going to make any sense without the lecture. So some quizzes you can sort of scan right through, not logs. But having said that, it's a pretty simple concept. So let's see how I would go with it. First, I just want to check some indices. Just powers. Indices just meant to the power of. Just want to confirm that we're okay with some of these, because logs is just another way of talking about powers. This was a rule from last semester, which again, you might have just come in, but this is a required knowledge. So if we said 3 squared times 3 to the 5th, it's just 3 to the 7. And the way we could picture that was saying 3 squared was a 3 by 3. 3 to the 5th is a 3 by 3 by 3 by 3 by 3. So if they're all multiplying, you can see you've got 7 3s lined up. Okay? It's tempting to say, well, shouldn't that 3 by 3 become a 9 to the 7? No. It's just 2 and 5 3s. It's 7 3s. Another rule we had last semester was, so times would just add the indices, a divide and we'll just subtract. It was like putting 6 3s on the top and 2 3s on the bottom, and 2 of them could cancel. It just left me with 3 to the 4. So we would multiply 2 separate ones and add them. We would divide and then subtract them. And the other things are just confirming. Remember 2 squared, it's 4. 2 cubed, it's too easy to think, oh, 2 by 3 is 6. No, remember 2 cubed is 2 by 2 by 2. 2 by 2 is 4, by 2 is 8. 2 to the 4 cops another times by 2. So you can see the pattern in there. Times 2 again, 2 to the 5 is a 32, and so on. 2 to the 1, does anyone remember what that came out to? To the 1, just left it alone. 2 to the 1 was itself, and 2 to the 0 was 1. Yep. So, and look at the trend again. It's just nicely laid out that everything, 1 times 2 times 2, that was our run. That's what we need to just bring back a little bit of that in logs. And it goes on with 3 to the 0 will be 1, 3 to the 1 is itself, 3 squared, 9, 3 cubed, times 3, and so on. So let's go into logs. First, what is a logarithm? The wordy thing, so I've got a shortcut way, a nice way to remember it, but we've got to go through the words. A log is defined as the power to which a base number must be raised to produce a given number. Horrible. But that's a question we'll get asked. Log 5 of 25 equals. We call that little 5. It's not a power, it's a subscript. That's a base. Logs are the base 5 of 25. It's asking me a question, obviously. And the question it's asking me is, what is the power which that 5 has to be raised to give 25? In other words, when I read this, all I'm reading is 5 to this power gives 25. If we look at 5 to what power gives 25, again 5 might jump out, because 5 times 5, but no, 5 to what power? 5 squared. So it's asking, what power have I got to raise this little number to till it gets to there? So there's our base number. So the answer was 2. If someone asks you what's log 5 of 25, I think of it, you're saying what power do I have to put the 5 to get 25? And my answer is 2. Log base 25 is exactly the same as number 2. So they're equivalent. Log 5 25 equals 2 is the same statement as 5 squared is 25. This is the thing which I reckon helps. When I look at logs, all I think is left to the right equals middle. So here's my question. All I look at that is I say, what's on the left? The most left number is the 5. The most right number is the 2, and the middle is 25. Yep, totally agree with that. 5 squared is 25. Left to the right equals middle. If someone asks me what's log 3 of 9 equal to, I don't know why it's doing that line thing. but I'm saying that equals to something. Well, that question is exactly the same as left to the right equals middle. The thing on the left is a 3, the thing on the right is, I don't know, and the number in the middle is a 9. It's saying, what would that question mark have to be? And again, it's a squared. 3 squared gives 9. So if you've got left to the right equals middle, and this is when we write it starting with the log. If we write log something, blah, 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 it's always left to the right equals middle. So the logarithmic form is just when we write stuff like this. Write in log form. Log base 525 is 2. The exponential form is just the way that I'm more comfortable looking at it. The left base to the right power equals number in the middle, or 5 to the 2 equals 25. So if you ever ask for a logarithmic form, it's just the one with the word log in it. The exponential form is just the power form of the exact same thing. Let's do some examples and just see, well, okay, what are you talking about? What sort of stuff will we do? That. Okay, express log 416 equals x in exponential form and then solve for x. Normally the question would just say, find x. But the way I'm going to do it is write in exponential form. I'm much more comfortable with it. Left 4 to the right x equals 16. So if I want to solve for x, I've just got to look at that and think 4 raised to what power will give me 16. I know 4 squared gives me 16, I'm done. I can see that the x must be a 2. We've just got to continue to stop ourselves and thinking, well, 4 times 8, it's not times, it's a power. 4 to what power will give me 16? 4 squared will give me 16. Again, 3. Now, you don't have to write it out. I'm just going to write it out here. This is what's going on in my head. 3 to the what? That's just meant to be an empty box. Left to the right equals middle. 3 to, I don't know, equals 9. It's got to be a 2. 3 squared is 9. So log 3 nines are 2. Same thing going on here. Again, it looks 6-ish, I don't know. But no, that says 6 to the, I don't know, equals 36. And again, it's just a squared. Clearly, if in doubt with a log question, just write 2. But we're going to have better approaches than that. Well, this one's not 2, finally. What's that one going to be? Yep, 3. 2 to the what power gives 8. Remember, it's just asking how many 2's have to get lined up. 2 by 2 is 4 by 2. Yep, 2 cubed is 8. And log 2, this statement, log 2 8 equals 3, they're exactly the same thing. Log 2 8 is just asking that question, what power? It is equal to number 3. I can't do some algebra where I subtract log from both sides. This isn't something... The log 2 8 is a thing. It's a unit. I can't just, let's halve the 2 out of it, or let's remove the log. No, I need to answer that in one go. And also, let's note the calculator as well. The calculator's got a log button on it. It's log base 10. Like the calculator, I think we come to it later. But if I asked, what is log base 10 of 100? What's the answer? 10 to what power gives me 100? 10 will get squared. Yeah, 10 squared will give me 100, because 10 by 10 gives me 100. If I can do that on the calculator too. Because the calculator button might only say log, but the calculator button is a log 10. If I press this button on the calculator, then 100, it'll tell me 2. But it doesn't have any other logs on it. Okay? The only other, the ln button next to it is natural log, which is a base e, which we don't touch. Okay? It's one of those, it's like pi. It's a 2.7, blah, blah, it's not for us. I'll admit some calculators now come out with other bases, but it's rare. Okay? The FX82s and all that, they don't. So if you're looking for the log button on the calculator to help you here, if it's log base 10, absolutely. But if it's not log base 10, it's not going to help. Okay? What else? Okay, same train of thought. Well, what would log 10 of 10 be then? 10 raised to what power leaves me with only a 10. 1 does nothing to it. Okay? 10 to the 1 gives 10. That's what it's asking for. 10 to the what gives 10,000. Well, just think of the trend. If 10 to the 1 gives 10 itself, and 10 squared is 100, 10 cubed must be 1,000. The power is the same as the number of zeros you got on it. So how many 10s do I need to multiply to give 10,000? 1, 2, 3, 4. That's the one the calculator will spit out for me, but I don't need it to do that. I can count the zeros. So 10 to the 1 is 10, 1 0. 10 to the 2 has got 2 zeros. 10 to the 4 has 4 zeros. That's exactly it. So that was 1, that was 4. Now this is asking 7 to some number equals 1. That was that strange one, yeah. The power of naught will always give you a 1. Your calculator will confirm that for you. Power of naught will always answer 1. The reason behind it was when we said stuff like, what's 5 to the 4 divided by 5 to the 4? I can say, look, whatever that number is, divided by itself, it's equal to the number 1. I promise you, anything divided by itself is 1. When we used our index laws, we said 5 to the 4 divided by 5 to the 4 equals 5 to the 4 minus 4. In other words, anything divided by itself is equal to itself to the naught. And itself to the naught is always going to be 1. So we've just got to lock in. Resource sheet, let the calculator confirm with us, but anything to the naught, 7 to the naught, will give me a 1. So we had, what was it, 1, 4, naught. Bit of algebra, x to the what gives x? Just 1. 1 is the thing that does nothing to it. X to the power of 1 just leaves me alone with x. X to the what will give me x to the 43. What's that, Taylor? No, don't do this to me. Just think, if I wrote it out, x to the power of what will give me the answer of x to the 43. If I wrote it that way, it looks a bit nicer. X to the what gives x to the 43? X to the 43 gives x to the 43. Okay? X to what number gives x to that? It's just the number. It's off-putting because it's algebra, but once I've written it in this form, and I'm asking you what's got to go in the box, it's got to be a 43. Can we answer that? It's back to the one above it, isn't it? Who cares if it's a 7, a 14, a Spider-Man, or an X? Anything to the naught equals 1. X to the what gives 1, to the naught. Anything to the naught gives 1. So yeah, we've got to dredge up some indices. Indices are the issue here, not logs. The only way logs are an issue is if you don't know that means 6 to the what gives 36. Once I've got that, it's an indices question. At least we've got the calculator to check our answer. Find the pronumeral. That just means find the letter, the variable, okay? So it's exactly the same concept, left to right equals middle, but instead of asking me what's this one, it's asking me what's this one. But my answer is still just going to be write it out the way I'm used to. Please write in its exponential form. Left to the power of the right equals middle. What's the x going to be? It's got to be a 9. You could go on a technicality here and say, what about minus 9? Minus 9 times by itself to give 81. We don't have negative bases, okay? It's a concept that I think we look at it later, but yeah, we don't do it. It's not useful for us. This is applied stuff. We only want the positive answer, so it just simplifies it. The only answer we care about here is, what's the x? It's a 9. What about another one? Okay, log x8 equals 3. That looks a bit horrid, but when I write left to the power of the right equals a middle, that's hopefully on our spectrum of things that are nice when they're cubed. 1 cubed is 1, 2 cubed is 8, 3 cubed is 27. That's one of them. It's 2. What number when times by itself 3 times will give me 8? 2 will. Log x81 equals 4. That's another one that hopefully is on our list of fairly nice ones. At the top end, admittedly. Left to the power of the right. And I've got my calc, even if I'm just not sure, I could try. I know if I'm getting asked to do this, it's going to be nice. 2 to the 4, calc tells me it's only 16. 3 to the 4, that's 81. Okay? 3 by 3 is 9, by 3 is 27, by 3 is 81. Even if your resource sheet had a few of the nice ones, like if I wasn't liking this, I would write on a resource sheet that say 2 squared is 4, 2 cubed is 8, 2 to the 4 is 16, 2 to the 5 is 32. have some 3s and 4s there. 3 squared is 9, 3 cubed is 27, 3 to the 4 is 81. Maybe some 4 squared, 4 cubed, 4, 4. A 16, a 64, and a 256. Okay? Even a bit of cheat sheet like that, but you've got your calc. Okay? Okay, now the unknown has moved to here. Ironically, this is the easiest one of the lot. Because that just says left to the right equals middle. 7 to what's on the right, 2, equals what's in the middle. All I've got to do is go to the calc, or work it out. X is 7 squared. 49. Wasn't too rough. Same here. Okay. Left to the right equals middle. 2 to the 4 is 16. So X is just 16. This one's going to wreck my box. Okay, it's a challenge one. Let's just write it out. X to the right equals the middle. So that's a bit nasty. I'll admit it's a bit beyond where we're going. It's just if you've got a good memory on indices. It's what to the power of -1. Again, this is last semester, okay? This is more, instead of challenge, I could have just written fun, okay? -1 meant 1 over. So 1 over x equals a half. If I write it that way, it's a much easier question. You can see the x will be a 2. 1 on x equals 1 on 2. The x had better be a 2. Long story short, 2 to the power of -1 is a half. But it's challenge. Don't worry about that one for our content. So, there's a base of logs. Relevant question. Why? Why use them? Neil's watching, okay? Not example stuff. So a Scottish bloke, John Napier, came up with it, and it was for a very practical reason, and it was just to speed up multiplication of numbers. We'll have a quick look at it later. But pre-calculators, logs are everything. Not in my learning time, but in my mum's, they had log tables instead of calculators. So it was the calculator, the way to speed up some pretty horrid calculations. We don't have to go there. Why do we care? Anyone going in a science direction is going to get very loggy, all right? Logs have natural applications, rabbit population, human population. We've got some practical ones in here. But if you go into the sciences, use pH, use anything with natural growth, it's going to get very loggy. It's not a bad thing, but logs are used all throughout there. And we're going to use logs to solve exponential equations, which aren't nice. We know 2 cubed is 8. We know 2 to the 4 is 16. But if someone said 2 to the what gives 10, I'd be stumped. But logs can answer that for us. So I've still got a real use for it, okay? We'll get there. This one, Neil is just watching, and again, it's a heads up for those going in the science direction. You'll do Math 1001, and Math 1001 is the lowest level of maths you can do in uni, but it's just for the sciences, and it's loggy. And again, I just wanted a quick glimpse at why. Why do logs to us? Well, if you look at this graph, whatever this data is, doesn't matter. But it looks like, look, nothing really changed, and then everything really took off. So when you graph x versus y here, it looks like these differences are absolutely petty, meaningless. Sometimes in science it's not true. Those differences mean everything. So if we plot it versus log of y instead of just y, well, 10 to the what gives 1, 10 to the naught gives 1. 10 to the what gives 10, 1 does. 10 to the what gives 100, 2 does. And you see if you graph it that way, log 10 versus x becomes a graph that shows these set differences. Math 1001 takes over from me there. I won't go further. But yes, we use it to straighten out graphs. Richter scale is the only applied thing we're going to ask you questions about. I'll have a quick look at pH, quick look at decibels. We're only going to ask you about Richter scale. And again, it all comes down to one nice little shortcut, which I'll say in a second. But we've all heard of the Richter scale. It's to do with earthquakes. It's telling you how severe was the earthquake. And these are one of the things that are best looked at on a logarithmic scale, because the differences in magnitude of earthquakes is so massive. It may look at the bottom end like, oh, nothing's really happening, it only happens here. The truth is, all these earthquakes can still be very significant. Even the first ones that look really flat, they're all quite significant. There's the olden day scale. So I talked about wherever you've got this seismograph that, however, whatever millimetres it peaked there, you'd match that here. How many kilometres are you from the centre of the earthquake here? Draw a line, it'll give you a magnitude and say, well, that was 5 on the Richter scale. Great, okay, that's a Richter scale. But how do we actually interpret that number, 5? What's that telling me? 5, is that big, small, what? Well, that's the manual scale. This is not the examinable content. Okay, we're not going to say how severe was this earthquake. But you can see there, okay, a 2 or a 2.5 isn't even felt. A 5.5 to 6 got slight damage, but we get to absolute devastation, 8 or greater. So these things actually jump up a hell of a lot between Richter scale readings. How much? Well, if we think of a reading of 5 as 10 to the 5, now we're talking. A log scale got done to the Richter scale and basically it was all 10 to this number. So if we talk about a magnitude of 5 on the Richter scale versus magnitude of 4, we're comparing 10 to the 4 to 10 to the 5. 10 to the 4 has got 4 zeros. 10 to the 5 has got 5 zeros times 10. So 1 on the Richter scale is times 10. Okay? An earthquake of Richter scale 5 versus an earthquake of Richter scale 6. The 6 was 10 times stronger. So instead of being, oh, it's a tick up, no, it's 10 times stronger. If we then look at what about 6 versus 4, 10 to the 4 versus 10 to the 6, times by 100. Okay, it's 100 times more powerful, so it's massive. So a 10 to the 4 is like a birthday party compared to 10 to the 6, which is a genuine earthquake. Now, what do we need from that? What's the shortcut, I reckon? This is my shortcut. 10 to the diff. If you want to know the difference in magnitude between two Richter scale readings, between 3 and 5, it's 10 to the difference between the Richter scale readings. What's the difference between 3 and 5? 2. 10 to the 2, 10 squared, it's 100. Okay? That's all we need to look at any log scale, any genuine log scale. If you want to know how many times greater it is, it's 10 to the difference between the readings. Same with pH. What about another one? 4.5 and 4. Okay, it's not as easy. I'm not doing it in my head. But what's the difference between 4.5 and 4? A half. So my answer is 10 to the half. What's that? I'm just going to the calc. 10 to the power of 0.5. 3.16, let's call it 3.2, approximately equal to 3.2. So even the difference between a Richter scale of 4 and 4.5, it's 3 and a bit times stronger. Okay? But that's it, 10 to the diff. If we can handle that to interpret a log scale, that'll help you next year in Math 1001. Anyone going that way? Another one, genuine numbers, because we had an earthquake in '89. It was magnitude 5.6, and we still talk about it like it's a pretty big deal. When I was a lad. The Japanese one in 2011 was 8.9. Clearly a little bit worse than ours, just taken a bit of stuff off the Kent. No disrespect, because people died. I shouldn't downplay our quake. But 10 to the diff, well, it's an 8.9 minus a 5.6. So the difference in magnitude would be 3.3. So what, I know it's going to be a lot. 10 to the 3 would be 1,000. 10 to the 3.3, 1995. Close enough to 2,000 times stronger. So you can see, yeah, that result versus that result. Yeah, fair enough. Okay. So, 10 to the diff. Neil's back. Just want to show this is still 10 to the diff. For anyone doing chemistry that's maybe used pH before, talked about there's a pH of 7, pH of 14 and all that. That's already been converted. It's a log scale. pH is a concentration of hydrogen ions, but if we talked about a neutral solution, we'd say its concentration was 10 to the minus 7. But we just, and A strong acid, 10 to the minus 3, and a strong base, 10 to the minus 10. They're not nice numbers to play with. And like that strong acid, only 10 to the minus 3, that sounds pitiful. But you don't want to drink that stuff. Those little differences of the world of magnitude. What we did was call it, the pH is a negative log of the H+. So instead of referring to this as 10 to the minus 7, we called that pH of 7. We just took the power and the negative of it. Instead of calling this 10 to the minus 3, we called it 3. Instead of calling it minus 10, we called it 10. That's the pHs we quote. When we quote them, we're talking actually about something from a log scale. Before the transformation, you can see a 10 to the minus 10 and 10 to the minus 7 when written on the number line look like they're totally on top of each other. And the difference between them is just nothing. And there's the acid. But if we graph the pH values, neutral of 7, strong acid of 3, and strong base of 10, that's more realistic. So again, just giving background, why do we bother with logs? You've already used logs, you just may not have known it. We're not examining it though. Purely interest. And the last one's just a slide. There's more in the book, but I've taken out the lecture slides, so I don't want to be off-putting. The decibel scale is also, it's 10 times a log scale, but it's still a log scale, okay? Because the range of hearing we can have. We can hear a sound that corresponds to displacing particles of air by 500 millionths of the width of a human hair. Which does my head in, that we can hear that. The sort of sound that can move a bit of air 500 millionths of the width of a human hair. So we can hear things which are incredibly, incredibly soft. But we can also hear things 10 to the 12 times greater than it, like a billion times greater. So we need a log scale to deal with the massive range that we can actually hear. But again, we're not examining this, but logs we are still using. This is more what I want to spend time on, the log laws. And this is why I brought up those indices laws in that first slide to say, remember we did a bit of this. In the first slide I talked about stuff like 5, say, to the, I forget what numbers I used. Let's just say 5 to the 2 plus 7 was the same as 5 to the 2 times 5 to the 7. Okay? When we had two things and we multiplied them, we just added the powers. Log laws are exactly the same but opposite. And they can go on the resource sheet anyway. But here we were saying when we used to times indices, we would add the powers and bring it into 1. With logs, it's the exact but opposite. When I'm adding two separate logs, we bring them together as a times. So what used to be times became plus. Now we're going plus becomes times. It's a real, it hurts the brain a bit at first. Because also, just looking at that just looks like gobbledygook. It's only when you play with some numbers that you can see, okay, I'll see what you're on about. We'll give some examples. Log 10 of 100 plus log 10 of 1,000. Without even using that law, 10 to the what gives 100? Well, 10 squared does. 10 to the what gives 1,000. So really all I'm looking at is the question, what's 2 plus 3? Well, let's check this law. This law says that log 10 of 100 plus log 10 of 1,000 will be log 10 of these two multiplied together. They were separately, they were plus, so let's times them together. If I times 100 times 1,000, I'll get one with 5 zeros, which is 10 to the what gives that. So that's not a full mathematical proof, it's just showing that, look, yeah, the law works. Okay? If I am adding these two things, 2 plus 3 does equal 5. So if I need to add two logs, I've got to multiply the two together. Notice that it only works, this is an A, this is an A, this is an A. So this is a 10, this is a 10, this is a 10, all good. If someone chucked a 9 in there, all over. This law won't work. This law is only when you've got the same base. Let's look at another example there. Log 2, 2 plus log 2, 8. Well, the law tells me must be log 2 of 2 times 8. Log 2, 16. Stop. Okay, do I believe it? 2 to the what gives 2? 1. 2 to the what gives 8? 3. 2 to the what gives 16? 2 by 2 by 2 by 2 is 4. Yeah, I believe it. Okay, again, Log A3 plus log A5, I'm not going to be able to test it, but I already trust the rule. If it's a log A and a log A, my answer will be log A. And it says when you're adding them, times them. 3 5s are 15. Of course, log A8 is going to be an incredibly tempting, incorrect multiple choice answer. Log A3 plus log A5, it's log A8. It just doesn't work that way. If this made sense to us at one stage, this is doing exactly the same, just the other direction. So, on my resource sheet, I would have just something like log x plus log y equals log xy. Okay, I didn't write the base there, I'm just going, look, whatever the base is, but you've got it. The log x plus log y comes together as xy. That just reminds me, plussing two separate, come together as a times. Okay, last example there. This is an example of one that we can keep going with. 6 to the what gives 2, I don't know. 6 to the what gives 18, I don't know that either. But I can use the log law that says they're both log 6, so that's log 6, and 2 18s is 36. So notice from something that I couldn't answer, I've used the law. I can go further with that. What's log 636? It's a 2. Because if you read that as well, 6 to the what gives 36. It's actually a 2. I needed that middle step. I needed that law to get there. My calculator won't accept that input, and I couldn't work it out myself. It became a pretty answer, but I needed the law. So far, the annoying law is, in logs, plus becomes times. Ugh. But let's persevere. If plus becomes times, minus becomes divide. If I can accept the plus logs, make them times in there, I've got to accept that minus becomes a divide, same as the indices. So if that's true, that minus becomes a divide, well, my gut instinct might want to say 1,000 minus 100 is 900. No, it's still log 10 and it's a divide. It's a 1,000 on top, 100 on the bottom. Not equals, I didn't mean to write that equals in there, sorry. It's log 10 of that thing, which is log 10 of, well, 1,000 or 100 is just 10. Does that have a prettier answer? 10 to the what gives 10? 1. It's one of the rare ones I could check on my calculator if I wanted. Let's just check it here. 10 to the what gives 1,000, 10 cubed does. 10 to the what gives 100, 10 2 does. The question said, what's 3 minus 2? I'm pretty confident, without the calc, that it's 1. Okay, so there's our log rule. So it became log 10, 10, which is 1. What about this one? I could do it manually. 2 to the power of 4 gives 16, and 2 to the power of 2. All right, I'm pretty confident already the answer's 2. But let's use the law. The law says it's the same as log 2 of 16 divided by 4. 16 divided by 4 is 4. 2 to the what gives 4. Yep, agreed. So it was minus, so I did a division. Another one. It's got algebra in it, so I can't, even if I had one of those calcs, I couldn't do it. Should I have left that middle step in there maybe? If that sucked, I left the middle step out. I put the 16 on the 4. It became the 4. I'm making it worse. Log A, so I know I can't get an actual answer. All I can do is simplify this number on this number. 20 on 5 is 4. And why can't I go further? Because it's an A. A to the what gives 4, I don't know what A is. So I can simplify, but I had no chance of completing it if there's algebra left in it. Unless I got to, what if I got to an answer of log A1? Could I go further with that? That one I could. Because A to the what gives 1, that's the special one where who cares what A is? A to the naught gives 1. That's the unique one that, yeah, I could keep going with that. Or if I got to an answer of what's log AA? Well, if they're both A's, I can answer that. A to the what gives A? 1. 1 doesn't do anything to it. But log A4, nothing I can do with that. And the last one here, I can't do that in my head. 4 to the what gives 8. Well, it's not pretty anyway. 4 to the what gives 2. Well, it's actually a half but we don't need to worry about our fractional indices or negative indices. We're just going to deal with these nice ones. Log 4 to the 8 minus that, well, I'm just going to use the law. It's going to be a log 4. The number goes on top as an 8 and on the bottom is a 2. An 8 on a 2 is a 4, so I've got it down to log 4, 4. And be careful there, because if the question here will just say fully simplify. I mean, go as far as you can. I haven't gone as far as I can. If I selected that in multiple choice, I'd be wrong because it's not fully simplified. 4 to the what gives 4. So the answer to this horrible question is 1. You're going to find we're still going to get nice answers. It doesn't look like we're going to, but we're going to. So that's 2 log laws. When you're plus, you bring it together with times. When you're minus, you bring it together with divide. We've got 3 log laws. That's it for the new laws. We'll use them in a few different ways, but there's only 3 laws we're bringing in. Here's a random question which will still happen. Can we simplify logs with different bases? That law only works if that was log 2 and that's log 2, I can use the law. I can't use that law here. Can the question still be done? How? If that law doesn't work, how can we answer this question? Can we do, what is log 2, 8? 2 to the what gives 8? It's a 3. What's log 3, 9? 2. 3 to the what gives 9, 3 squared gives 9. It was doable. It looked like, yuck, but it was doable. So sometimes, yeah, we can do the individuals, sometimes we just can't. We've got to use the law. I couldn't use the law there, but it was still doable, all right? So here's the third law, which initially is going to look, well, equally as wrong. It's saying if I've got some log of something to a power, that power is allowed to move down to the front, which seems like, yeah, right, okay. It does. It does. Let's look at an example. And I swear after you've done a few of these, it gets to become a bit more natural. After you've done a few, but at first it just looks, can I really just move that? Let's look at this example. Log 10 of 1,000. Would you agree with me that log 10 of 1,000 can come from log 10, 10 plus log 10, 10 plus log 10, 10? Because the law was, if you add these things up, they come together as a times. Doesn't matter if there's 2 bits, 3 bits, 4 bits. But if they were to come together as 10 times 10 times 10, what I've written there is 100% correct. Okay, yes, you can split up into those bits. What if I ask the question, what's log 10 of 10 cubed? Well, all I've said here is 1,000 is the same as 10 cubed. And all I've said here is, if I've got a log 10, a log 10, a log 10, I've got 3 log 10 10s. They're exactly the same thing. We don't have to prove these things. I like to put these in just to say, look, okay, I can see that log 10 of 10 cubed will give me log 10 plus log 10 plus log 10, which is the same as 3 log 10, 10, 10. Log 10, 10. I said one more, too many 10s. That power is allowed to come to the front. Now, this doesn't mean that x squared is 2x. I'm not saying that whenever you see a power, you can bring it to the front. It doesn't change that, okay? 5 squared is not equal to 2 5s. This is only for logs, okay? If I've got log to the base 2 of 3 to the 4, it just says I'm allowed to call that 4 times log 2, 3. Okay, that's it. The third rule says log of something with a power, the power is allowed to come to the front. And whether I write times or not, it's a times. If I just wrote 4 log 2, 3, it's a times. It's the same with everything. If there's no sign there, it's a multiplication. So it might be a bit hard to swallow that, yeah, okay, that's true. But the third rule is just that. Log of x to a power, that power can come to the front, and it means exactly the same thing. So, with that example, log 3, 9 to the 7, if I was to solve, if I didn't use this law, I'd have to work out what 9 to the 7 is. 9 by 9 by 9 by 9. Woof. And then work out 3 to the what gives that massive number. Horrendous. But I'm allowed to say that power can go to the front. Does that make life easier? Yeah. What's log 3, 9? 3 to the what gives a 9? 2. So 3 to the 14 is the same as 9 and 7, but I avoided horrible numbers just by that little law that the power is allowed to come to the front. It made life much nicer. Let's check another one. Okay, this is a mixture. Once again, examples are the best way to do it. Evaluate without a calculator. Yes, you can use a calculator, but these sort of questions will come up, which means just give us some working, or and some of them you won't be able to use the calc anyway. Log 10 you can, but show your working. Well, there's not much needed here. I've got options. I could use my law, which said that's equal to log 10 of 100 times 10 is 1,000. And then I'll say 10 to the what gives 1,000, and I'll say 3. What's another way I could have done it? What is log 10 of 100? 10 to the what gives 100, 10 squared does. 10 to the what gives 10, 1 does. Doesn't matter which way you did it, as long as you got to 3. So in one way we've talked about using the first law. The other way I've just answered it. Another way, just to be a smart ass, I could say that log 10 of 100, well 100 is 10 squared. I'm allowed to do that. I'm doing it a long way, but just to prove a point, 110 squared is the same thing. Apparently I'm allowed to bring powers down the front. So that's 2 log 1010 plus log 1010. Well, collecting like terms, if I've got 2 of them and 1 of the same thing, I've got 3 log 1010s. And log 1010 is the number 1. Stupid way to do it, but just wanted to prove the point that this whole power to the front thing, promise, it's all good. And at times we just have to. Okay, but I'll go one of the first 2 methods. This one, okay, first let's try it manually. What's 10 to the what gives 10? Just 1. 10 to the what gives a number 1? That's that. 0, 0. 10 to the 0 gives 1. So what's this question really asked me? What's 1 plus 0? Clearly the answer is 1. I could have used the law. The law said if they're both log 10s, well, 10 times 1 is still a 10. Well, that makes sense. It seems odd at first. How can log 1010 plus something still equal log 1010? It's because that's a 0. Log 10(1) is a 0. So whether you did the 10 times 1 is 10, or whether you worked them out individually, great. Log 2 8 minus log 2 4 equals, well, I could still do it manually. 2 cubed is 8 and 2 squared is 4. Or use the law that says it's the same as log 2 of 8 on 4. Well, the log 2 of 8 on 4 is just a log 2 of 2. And again, 2 to the what gives 2. So are these. Maths-wise, they're not that bad. They're off-putting, not that bad. Without knowing a log, good luck guessing the answer, because it's so foreign. Another one. Here's the first one that I wouldn't want to do manually. 2 to the what gives 20, I don't know, it's not a nice number. 2 to the what gives 5, again, not pretty. But if I combine them, it's the same as log 2, it's a minus, so I'm going to make a divide. A 20 on a 5, it's the same as that question. Log 2 of whatever 20 on 5 is. It's a log 2 of a 4, that's pretty. 2 to the what gives 4, 2 squared gives 4. Okay, I didn't have a list of options there. I had to do it that way. A 3-piecer. I could do it in 1 go, I could do it in 2 goes, it makes no difference. Let's play safe and do it in 2 goes initially. And let's just look at, but I do want to come down to the all-in-one go thing. If I just wanted to combine them, what's a log 10 5 plus a log 10 6? It's a log 10 what? If we're adding to bring them together, we've got to do it times. And I'm still saying log 10 3. So all I've done there, I'm doing it in 2 bits, 5 6 or 30. Now the minus tells me do a division. It's now log 10, 30 on a 3. And you can see, yeah, it's going to turn out nice again. Because how many 3's in 30? There's 10. And 10 to the what gives 10. So that's the 2-step way. But note, with any of these, if you want to go straight for it, it's all good. If I've got to try and make all of them into one thing, well, I've got a 5, plus means times a 5 times a 6, and I divide by a 3. That's everything that's in the question. The plus means times a 5 and 6. The minus means divide. So 5 times 6 on 3, which is log 10, 30 on 3, which is log 10, 10, which is 1. Whatever you're more comfortable with. If you didn't mind going straight to it, great. Otherwise, just do it in 2 steps. We're not talking a heap of time difference here. One more here. Log 4 8 plus log 4 8. 4 to the second gives 8. It's not one of our pretty answers. So let's just combine them. Call it a log 4. 8 times 8 is 64. That might be on my resource sheet. There's some of the nice ones, but 4 squared is 16. 4 cubed is 64. So 16 by 4, yep, 4 cubed. 4 to the what gives 64? 3. Just note here for trivia's sake, they were both the same thing. Log 4 8 plus log 4 8. I could also say it's the same as 2 log 4 8. And if I'm allowed to bring a power down, I can go in reverse too if I want. That's the same as log 4 of 8 squared, which is log 4 of 64. No reason to do it that way. The first way was much smarter. But again, some things might jump out first. If you saw that, that's okay. We've got more of this stuff to play with and get used to. 10-minute break there. Do you want the phone or keep it charging? You got over your shock on Saturday? It's all good? Say it. You just talk to it. It just keeps walking. No, fine. No. I was, but it doesn't matter. Bumped into it in Jasmine, and he looked terrified. Sure.
Mid-semesters and seating them in different rooms. I've got to email you about that, don't I?
Oh, yeah, but you want it?
Yeah.
Then we're doing it, yeah. I've got it noted. And Yeah, get all that sorted.
I'll send you an email back in tonight just so you like see it there, I guess.
Yeah,
In case.
I've already made note of it, but yeah, it's all good. I'll try and arrange it at the same time as the lecture. As we're having extra more of that. Yep, it'll be sweet. If you're up for it, in week 8. If you're not, then
I'll let you know.
Can I hand this to you?
Yep. So that's why one. Yep. So it's that one. And that one. There you see, yeah. Yep. So this one. Cool.
Thank you.
Yep. So we're told, yep, B equals 4, A equals, don't know, and Y equals A equals perfect. So the actual info we've got, apart from B equals 4, is that this point works. That's an X and that's a Y. So if you can put that Y value, replace the Y, the X value, replace the X, the B, replace that, you'll have all numbers in the range. Yep. Hang on. The Y is the -5, not the X. And X is just a positive again. So -5 equals A plus 4 ones. So the 4 times 1 is just a 4. So -5 equals A plus 4. And you can rearrange that to get an A equals. Once you've got your A. Does that make sense? Because then, yeah, your 4 times 1 is minus 5 equals 8 plus 4. And to get the 8 by itself, take 4 off both sides. It's going to tell you that minus 9 equals 8. And also here, from your picture, which is correct, if it's got a gradient of 4, then the y-intercept thing will be 1 step across and 4 steps down. Yep, minus 9 seems pretty good. Yeah. Cool. So 12. Okay, why is the 12? Oh yeah. So you've got the 12 minus 3 is 4. So you've got a 12 on the top. There must be a divide by 3, but it's another times 4. So it's a 4 times 12 on the top, the 3 is on the bottom. Alright, some more examples. And again, some of these are going to have multiple ways to do it. Actually, I'll look at a potential trap here. My gut instinct here would be that power can come to the front. Okay, I've got a log 3 9 squared. Edward. Hello. Hello. I can bring that power to the front. 2 by log 3 9. That makes it clearer to me. Okay, that power was so 2 by log 3 9. Is log 3 9 something nice? Yeah, 3 to the what gives 9 is a 2. So it's a 2 by 2. Okay, it did work out well. But let me just note a potential trap here. That was the question. Log 3 9 might jump out as, well, you're easy to do. Log 3 9 is a 2. 3 to the what gives 9? Well, 2. Hence, I could do this. Oh, damn it. It works. That's a fluke. Oh, shit. Okay, this is a fluke. Okay. But I just want to make sure that we're not saying that, okay, if log 3 9 is 2, let's put it there and it's still squared. Because was the question saying all of this was squared, or was the question saying the 9 was squared? Only the 9 was squared, and unfortunately the example I picked to show you, it works anyway, but I promise you it's a fluke. So if you ever see a question that's, log 3 9 squared, just note, that is the bit that's squared. Okay, and if you wanted, you could say, well, that's log 3 81. well, you're right, equals log 381, but I've sort of made things hard for myself. 3 to what power gives 81? Ugh, not nice. It is 4, we know it's 4, but it was much easier spotting that 2 and saying, look, come to the front. Okay, so you might have multiple ways of doing it, but I would always get a power and bring it to the front, and it makes it nicer. Again, I'm going to do it here. I could, oh, okay, there's options. Can anyone see the answer? 5 to the 5, log 5 is going to be a 1, so it's going to be 7. So maybe you'll bring the power to the front. If you brought the 7 to the front, it would become 7 times log 5. Log 5 is the number 1. 5 to the what gives 5? It's a 1. It's 7 times 1. It's 7. But also, I might have read that as said 5 left to the power of what will give me this. That would have done the job too. 5 to the what will give me 5 to the 7. 7. I still stand by the first method. I still think it's much nicer to bring that power to the front. And again, remember, only if there's a log there. We can't bring other powers to the front, but when there's a log there, we can. Simplify. Okay, it's algebra, so it's not like evaluate. Like if the word evaluate just means you're going to come to a value. As in the answer might be 7 or 12 or whatever. Simplify. We'll still go as far as we can go. There's not much we can do. Anyone see the only thing we can call this in a bit simpler? Log x of 10. That's it. That's all we can do. It's still a log x, and I can't answer to you x to the what gives 10. I don't know. What's x? Now this one. Log n 12 minus log n 3 plus log n 4. Again, maybe 2 steps is a nice way to go. Let's check it first. If we did in 2 steps, well, the log n 12 minus log n 3, the minus tells me divide. That's log n 12 on 3. And I know I've still got that at the end. The 12 on 3 is a 4. So it's log n 4 plus log n 4. What's log n 4 plus log n 4? 2 totally acceptable answers. 3 actually. I could say, that's like saying what's x plus x, and I'll say it's 2x. So if you want to answer it, what's log n 4 plus log n 4? That's 2 log n 4. There's 1 correct answer. Any other answer someone might have gone to? Log n 16? Same answer. Or I could have said it's the same as log n of 4 by 4 is 4 squared. When we say simplify, 3 bits down to 1 bit, that's simplified. But which of them is the simplest form? None of them are any better than each other. They're all great, okay? But if you can see, they're all the same thing. On this one, the 2's at the front. On this one, the 2 went up here. On this one, we've said 4 squared is 16. They're exactly the same answer. And especially when we're talking multiple choice, that's a really good example to say they're all the same. 2 log n 4, log n 16, log n 4 squared, all perfect. Okay? Alright. More. Oh, and I was going to say, yes, it still could have been done in one go, but just be careful. If you wanted to do them all together in one go, I'd have to say, well, it's a 12 divided by 3 and times a 4. So the minus refers to the 3. So if I said it's a 12 and we've got a times 4 and I've got to divide by 3, no problem. I think it's risky. I think I'd rather go approach it in 2 steps like here. But that's the truth. Plus that, they're on the top. Minus that, it's on the bottom. 12 times 4 is 48 on 3 is 16. So yeah, we can do it. It's just probably room for errors. Okay, simplify. Any preferred options? I would still bring that 3 to the front and look at that go and look. I'd rather say your log x2 plus 3 log x2. Yep, I just went third law. Okay, that went well. That power can go to the front. If I've got a log x2 plus 3 more log x2s, how many log x2s do I have? I've got 4. So oh yeah, okay, so that's a good answer. Or someone might have said, look, I've got log x of this, I've got log x of that, can't I just multiply them? Yeah, you can, which is log x, 2 times 2 cubed is 2 to the 4. Again, it's the same answer, isn't it? Whether the 4 is up here or whether it's down the front, it's the same answer. But no, this thing here, this thing about multiplying them, log xa plus log xb equals log xab. Alright, that's what we said it was. If you got that plus that equals that, fantastic. But notice here, if I've got a number at the front, that's different. Alright? Sure, log of this plus log of that was just log of this times that. No problem. That's what the law says. But if I just chucked a 4 in there, I don't use that law anymore. Okay? This law is only for log something plus log something, not log something plus 4 log somethings. Okay? We'll have a question on that soon. Okay. The option without moving the powers is all minus tells me to do is divide. So it becomes a single log, this divided by that. Well, this is a 4 to the 6, and that's a 4 to the 5. What's 4 to the 6 divided by 4 to the 5? There's 6 4s on top, and there's 5 4s on bottom. How many is left when we cancel? Just one solitary 4. Or 6 minus 5 is 1, 4 to the 1. Whichever way you look at it, it comes down to log y of 4. But I still stand by my gut instinct is, don't like powers, bring it to the front. Bring that power to the front is 6 log y4. Bring that power to the front is 5 log y4. It's a little bit easy, isn't it? 6 of those things minus 5 of those things is just one of those things, which is a log y4. 6 log y4s minus 5 log y4s is a solitary log y4. Either way. Is anyone agreeing that logs are sort of fun yet? Okay. Alright. Bash Chantel later, everybody. I like it. Okay, it's a sickness. Okay. Log 5 of 50 plus log 5 of a half. Looks horrible. I bet it comes down to a nice pretty number. I can't do that. Again, how tempting does it look to think that must be 10? I can see it. 5 to what gives... Oh, it's 10. No, it just isn't. 5 to the what gives 50? I don't know. 5 squared is 25. 5 cubed is bigger, 125. But we can use our law. Log this plus log that is log of this times that. And 50 times a half. Yep, it is nice. The 50 times by the 0.5 gave me the 25. And then 5 to the what gives 25. Okay, it did come down to a 2. Okay. All these initial ones are going to have nice answers. I admit we get to a stage very soon where we go to the calc and get decimals, but all these log simplifications are going to be nice answers. No calculator needed in any of them. This one, log 240 minus log 25. Well, that is going to end up nice again because the 40 on the 5 is an 8. It's a minus, so do a division, and a 40 divided by 5 is 8. And again, 2 to what power gives 8? 2 squared is 4, 2 cubed is 8. Works out nice. How many? Is that the last ones? Still more. Carried away. Okay, hey, okay. This is a good one. I can't use that first law because that 2's in the way. The first law said log of this plus log of that is log of this times that. But there's a 2 in the way. So I can't just call that 2 log 6, 12. It's just, I can't. So given that that 2 is in the way, and I don't want it there, any suggestions? reverse of what I kept doing to all the other ones. I kept getting powers and chucking them to the front. Well, if I'm allowed to chuck a power to the front, am I allowed to get a front and chuck it to a power? I must be. It's the same thing. And normally I said, yeah, I don't want the power there, I want it to go to the front. In this case, it's stopping me from doing the law. So what I'm saying is, I'm going to do the opposite. It's the same law, it's the third law. Log 6.3 squared plus log 6.4. I can do that. I just brought the 2 to the top. And I can do that. Remember, it's not the log 6.3 squared, it's just the 3 getting squared. So that is just a 9. You didn't have to put that middle step in, whatever, but 3 squared is 9. So really the question has become this. Instead of the 2 being at the front, it became a 3 squared, which is a 9. Now I can use my law. Log of this plus log of that is log of this times that. And 9 fours are 36. And again, don't stop there if you can go further. 6 to the what gives 36. So yeah, that was the same law, but just back to front. And here, I'll be doing the same thing. I've got no like terms here. I've got a log 3, 6 and a log 3, 2. It's not what that question says, what's 3x minus 3x? It doesn't. The answer's not naught. It's 3 of these minus 3 of those. But if I whip those fronts to the powers, then I'll use my law. Let's take that front to a power and that front to a power. It's going to become log 3 6 cubed minus log 3 2 cubed. So the 6 and the 2 got cubed. The numbers might get largish, but we've got our calcs now. So log 3, 6 times 6 is 36, times another 6 is 216, minus 2 times 2 is 4, times another 2. So it became log 3, 216, minus log 3, 8. We know that a minus means do a division then. So it's log 3 of 216 on an 8, which is log 3, 8's into there, 16, 5, 7. And again, I know, things look good. 3 to the what gives 27, that's one of my standard questions. 3 squared may be 9, but 3 cubed is 27. So, literally, log 3, 27, saying 3 to the what gives 27, I just go 3. Alright. Intermission. Just for interest's sake, so again, why was it useful? Why was a log chart, or what is a log chart, and why were logs calculators before we got calculators? It was just to speed up multiplication. We can bring it up now because the concept is that first law we just did. If someone in the olden days wanted to do 1.4 times 1.9, where there's 14 times 19 and all these, they had different ways of dealing with decimals. But say they wanted to quickly do 1.4 times 1.9 without even doing long multiplication and anyway. Well, that was the first law. We said log of an x plus log of a y became log of xy. Okay. Which in reverse says, if you got log of two things times, you can split into 2 bits. And Neil's watching, just want to make it clear. This is interest. He's interested. Oh, Neil isn't watching. He's here. Okay. So if log of xy can be split into 2 things, that means log of 1.4 times 1.9 could be the log of 1.4 plus the log of 1.9. That's what I mean. How can log tables be used to do a multiplication via additions? It turned a multiplication problem into an addition problem. Then they'd have to go to their log chart and say, well, what is log of 1.4? In this case, I should have actually written log 10s. We're going to use, if you don't write, I think it says later in the notes, if you don't write any letter, it's assumed you're calling it 10. Like the log button on the calculator is log base 10, okay? So if you don't write any letter or number, it's log 10. So log 1.4, what's that? Log of 1.4, you'd go to your table and say log of 1.4 is 0.1461. What's log of 1.9? Log of 1.9 is 0.2788. And then we'd say, instead of multiplying, just add them. So log of that times that is equal to 0.4249, and then they'd have to find that number in the table and then see where it came from. It came from 26, and this is its decimal part, and it gives an answer of 26.6, which had to come back 2.66. Yuck. Calculator. Awesomeness. Okay? But that's exactly what they use it for. Standard calculations were done. Turn the times into a plus, do it, find the answer in there, and there's your answer that you must have started with to the initial question. So yeah, I'm glad I never had to grow up with them either. So, what's our last reason for doing logs? And this is our last reason, and I think you'll find it fairly logical. Flows on using the laws. Let's find out. Logs can be used when you need to solve an exponential equation, as in one where the unknown is in the power. 3 to the x, okay? Solve 3 to the x equals 8. Now we know two nearby answers. 3 to the 1 is 3 and 3 squared is 9. So if someone's asking me 3 to the x gives 8, I can promise it's between 1 and 2. It's probably 1.8-ish, 1.9-ish. But we're going to use logs to solve exponential equations where the answer's not pretty. And we want the exact answer, but it's not a whole number. So, knowing that the answer is going to be about 1.8-ish, 1.9-ish, let's check it. 3 to the x equals 8 is our initial question. We look at it and go, that's not pretty. Now really what I'd like, if I want to solve this and find x, I want to get some algebra that can get this to an x equals. But it's trapped in the power. Why bring logs in? If I bring logs in, I can use that third law. Once I'm using logs, a power can come to the front, but not if there's no logs. So what we do is we take logs of both sides. Literally write the word log in front of the left and log in front of the right. If left equals right, log of left must equal log of right. It's got to be the same. But you can see now, why bother bringing logs in? Why make an easy question hard? Because now I'm allowed to use that law. Okay? Now I can say that x times a log 3 equals log 8. And then that's pretty simple algebra to say if I want the x by itself, the moment it's being times by log 3, if I divide the left by log 3, and notice I'm not bothering to write 10, these are just log 10s. Okay? If I divide both sides by log 3, it's going to be gone. X equals log 8 on log 3. And I've got a calculator on the button to do that. Literally, I just say x equals log 8 divided by log 3, 1.89 to 2 decimal places, okay? I'd already guessed it was about 1.8-ish or 9-ish. That's it. That's how we do it. So using logs, we had a practical use and we found an unknown power. Let's go through another. Oh, also clarify. So your log button is. So when we say log x, we just mean log 10x, and your log button on the calculator is the only button we care about, and only for log 10. The ln button, admittedly, well, most people call it in or in, but it's an ln. It's logarithm natural, it's in French-wise, but anyway, it's log ex. And we just don't care about that in this course, and Math 1001 doesn't use it either. Okay? 1002 and up use that. Don't care about the ln key, we just don't care. Example, I said that one before. So yes, we can use it for that. We'd expect the answer 3, and the calculator would give it to us log of 1000 equals 3. All right. Now, estimates. It's always nice to have some rough idea, especially when using logs and getting a bit complicated. Roughly, which one of them? 2 to the x equals 10. We've just got to think of answers around it. Like, I know 2 to the 0 is just a 1. 2 to the 1 is a 2. 2 squared is 4. 2 cubed is 8. 2 to the 4 must be 16. 10, which one's closer? About 3.5. Okay, so it's just, we have some questions. Look, roughly, was the answer going to lie? As long as we can work them out, get some close answers, I'd expect the answer to be about 3.5. Yep. So let's just, actually I'll just check it while we're here. 2 to the x equals 10. I'm just going to go through exactly the same steps. Actually, I'll write it over here. if I wanted the exact answer, see how close my guess was. I wanted to get the x down. I want to bring in logs. Log of the left equals log of the right. I now know I can bring that power to the front. So x times log 2 equals log 10. Actually, a good example. Now, if I want the x by itself, it's being times by log 2, so let's divide both sides by log 2. You don't have to write that little note I'm doing there, whatever you prefer, but that got rid of it. Equals log 10 on log 2. Now, the big mistake here is, doesn't that look like it should be log 5? A log 10 or log 2, it's not. It just isn't. There's no law. We never used a law that log something divided by log something. We had log something minus log something, but there's no law. That's just got to go to the calculator as is. It just, as much as it looks like it, that is not equal to log 5. Just go to the calculator as is. It's log 10 over log 10 equals divided by log 2 equals 3.321, 3.32 to 2 dp. All right, I had the closest answer. All right, so there's our technique. So our lecture examples, the last few left, it's the same stuff, with a little twist on one of them. It's minor. 5x equals 30, estimate answer first. Well, 5 squared is 25. 5 cubed is considerably bigger. I don't even have to go be accurate, but clearly it's 2 point something. 2.1-ish. Just so if I get an answer that's 17, I go, I don't think it is. I know it's 2.1-ish. It's definitely between 2 and 3. End of story. So to have, because it's a 30 in between these two. I want to solve this properly. I'm going to write log of the left equals log of the right. Cool. My power is allowed to come down to the front now. Yeah, that'll do. X times a log 5 equals log 30. So that's purely power to the front. Divide both sides by log 5. Gives me x equals log 30 on a log 5. Don't try and call it log 6. We know I've just got to go to calc. Log 30 equals divided by log 5 equals 2.11. Yay me. Okay. We'll check another one. It's the same technique. So make sure I'm not going through too quick. Here's where I say that, look, you might see a shortcut. And if you use this shortcut, it's totally fine. All right? It's your decision. But you can see those answers look like, all right, 4 to the x equals 25. I'm going to take logs of both sides. I'm going to have a log of 4 and a log 25 in the answer. But I remember it was always a division. Now I've got some idea. Do you want to see which one it's going to be? A. It will be, because once you take the log and the x, the log 25 is staying on the top, isn't it? The x on the left, it's going to be divided by. So if you spot that the answer to this question will always be x equals log of this thing on the right over log of this thing, then you're totally right. A lot of people will go along and realise this and go, oh, can I use this? Yeah, absolutely you can. It's nice to know the working in case it's a written question that requires working. But let's just confirm. How did I know the 25 went on the top and the 4 on the bottom? Just from the manual approach. I want to get at the x. I need logs. Log for the x equals log of 25. Now I can bring the x to the front. X log 4. And that's why you can see, yeah, this is the thing that's always going to have to move. The thing on the left is always going to have to move to the right. If I divide both sides by log 4, it's always going to be this thing, log of this on top and log of that on bottom. So definitely A. If you want a shortcut, your business. But don't lose the steps on the way in case it's a written question. All right. Estimate answer first. Okay, it's really the last. We've only got two left. This one, it's the other one with a twist. 7 to the x equals 20. Well, 7 squared is too high already. 7 to 1 is 7. 7 that's squared is 49. I don't know, somewhere in the middle. 7.5-ish. Sorry, 1.5-ish. I'm looking at the wrong thing. If to the 1 is 7, to the 2 is 49, then it's somewhere in between them. I wouldn't be surprised if it's 1.3, 1.7, I don't know. Somewhere between them. Take the log of the left. Take the log of the right. Bring the x down. And the final step is to divide both sides by the log 7. So it's a log 20, it's over a log 7. And what is it? Log 20 equals divided by log 7 equals 1.54. Yeah, okay. So again, I'm really confident if I'd already estimated the answer. If I accidentally got upside down, my estimate's going to tell me that hang on, something went wrong here. Okay, last one, which is particularly useful. We use this last bit, we use constantly next week. Same old each time, but we use this technique constantly next week. But next week, it appears this way mostly. And this week, we still need to know that. 5 times 4 to the x equals 100. The big trap here, and a lot of us are going to do it, is to say that is equal to 20 to the x. But it's not. Because BODMAS says, do your power first. Like if I said, what's 5 by 3 squared, I can't call that 15 squared. What is 5 by 3 squared? It's 5 by 9, which is 45. So the power's got to get done first, and then you multiply. So 5 by 4 to the x, I can't do the multiplication first. It just does not equal 20 to the x. As tempting as it is, just doesn't. So what should I do first to simplify this question? Divide by 5. That 5 is annoying. If we just divide both sides by 5, that's totally acceptable. That gets rid of that. It becomes 4 to the x equals 20. And now it's exactly like the previous page. I couldn't emphasize that enough. That's going to catch us. But if you've got, only ever bring logs in. If you've got something to the x equals something else, that's log time. That's log o'clock. If you've got 6 times, it's not. You always want to get rid of it. You want to get it in the simplest form possible, then it's log time. Don't try writing log here already, log here. Messy as hell. Simplify your question first. So your next step here is absolutely 105 is 20, then do the rest of the stuff. Log of the left equals log of the right, bring the x to the front, divide both sides by log 4. Don't fall into the trap of thinking, well, that's the same as log 5, because it's not. Just stick the log 20 equals divided by log 4 equals 2.16. And we're done. Admit, that was fun. No. I'll just say, is there a mic here? Hang on, I'll just do that. And don't forget, there's clinic on at 1 o'clock. Anyone that wants clinic, there's clinic today at 1.
I think so.
Sure. I think.
For this one, when you have like a something, you go like two to class one.
Yep.
Would that be 4 for the power of 4?
Exactly, choose the power 4. The bottom's 2. That's saying 2 to the 1, here's a 2, here's 3 2s, 2 to the 4.
Okay, so
Perfect. Yep. Cool. Welcome, Alex.
Am I right to give my quiz redemptions back to you, say next Tuesday,
Yeah. What, this week's one?
tutes or?
Yeah, that's fine.
No, I've got from week 3 and 4 that I want to do.
Yeah, that's cool.
Is that all right?
Yeah, too easy.
No worries, thanks, mate.
So yeah, we got a visit from Lily the other day, even though she's left. What's your 20? What's your 20 English? Social inquiry. Okay. So I confess I was getting cut up and I saw a voucher when he was burning. And I saw a general voucher. Yeah. And she asked what your 20 unit was. And I said, actually first she said, are you doing art? But you can't be doing art, can you? Yeah, because you couldn't take that as a 20, and you got this routine, you got lit, so you couldn't be. And I said, social inquiry. Yeah, wasn't coming to me.
Yesterday I found out my cousin was back in Logarithmic Form, and this is the cousin I so, last night I just fucked now.
Okay, so that was a. I won't say it's a plus. It's a rational. I mean, are you having irrational depression at the moment?
I was feeling a little better about the irrational stuff. It doesn't feel as dire as it did, the irrational stuff. It's kind of gone. Now it's just me trying to focus back on, getting through my work and whatnot. But tonight I think I'm just going to have to try and have an early night.
Yeah. Sometimes it's just.
Because I didn't. It was one of those nights where you're not sure if you're awake or asleep because you're just so tired and you're trying to fall asleep.
Yeah.
I got up at 6. I was like, fuck.
That wasn't the night's sleep. And you moved on to the new meds and stayed on them?
Yeah.
Okay, good.
Don't have any dosage increases for that for a while, but I went from 30 micrograms of Ritalin long release to 20 short release, and now I'm at 40 short release. So the difference is with long release, you take that basically once in the day, and then it covers you. It's supposed to cover you for the rest of the day. The short release is more, you feel it not immediately, but almost immediately. So within 10 minutes, maybe 20 minutes of taking the pill, you feel the effects.
Okay.
And now I'm on 40 of those, and the maximum of those you can take a day is 60. So I'm on a lot of it.
But you also got put on a new antidepressant. Yeah. That was the change because the Ritalin one happened.
Yeah.
But what's that one?
It's only very low for that antidepressant, but
But do you know which one it is?
it's a Telegram. Yeah, apparently it's the one that everyone hates. Yeah, so I was like, oh, thanks. Really? I'll see you.
Oh, yeah, yeah.